Hello, everyone. Welcome to our pre-calculus end-of-course review. I'm excited to have you here today. In this presentation, we'll be going over key concepts and topics we've covered throughout the course. We'll review important ideas and prepare you for what's next. Let's get started. Let's explore the distance between 2 points. Understanding how to measure this distance on a coordinate plane is a fundamental skill in analytic geometry. This concept really bridges algebra and geometry, allowing us to calculate exact measurements using just the coordinates. The key tool here is the distance formula, which is actually derived from the Pythagorean theorem. It gives us a powerful way to find the straight line distance between any 2 points in the plane. Grasping this idea is essential because it sets the foundation for many other concepts we'll encounter in this course. So, as we move forward, keep in mind how these measurements connect algebraic calculations to geometric intuition. Let's talk about how to find the distance between 2 points on a coordinate plane. First, we need to identify the coordinates of each point. We'll label them as x1, y1, and x2, y2. For example, if we have points at 2, 3, and b at 5, 7, then x1 is 2, y1 is 3, x2 is 5, and y2 is 7. Next, we apply the distance formula, which is d equals the square root of the sum of the squared differences in x and y, that is, d equals square root, x2 minus x1 squared plus y2 minus y1 squared. This formula actually comes from the Pythagorean theorem because we can think of the horizontal and vertical differences as the legs of a right triangle. Finally, we perform the calculation, subtract the coordinates, square those differences, add them together, and then take the square root. The result gives us the straight line distance between the 2 points, measured in the same units as your coordinate system. And remember, this formula works no matter which quadrant your points are in. The order of subtraction doesn't matter because we're squaring the differences, which makes the result always positive. This concept is fundamental because it applies universally across the coordinate plane, helping us understand distances in a variety of contexts. Let's talk about the midpoint of a line segment. The midpoint is the point that lies exactly halfway between the 2 endpoints. Think of it as the center point of the segment. Finding this point is really important because it helps us divide segments, locate centers, and solve various geometric problems. Now, there's a handy formula called the midpoint formula that makes this calculation quick and easy. It works by averaging the x-coordinates of the endpoints and doing the same for the y-coordinates separately. Imagine the midpoint as the balance point of the segment. If you place the segment on your finger, it would balance perfectly right at the midpoint. So, understanding this concept helps us see how segments are divided and how to find their centers accurately, an essential part of our overall study of geometry. Let's take a closer look at how to find the midpoint of a line segment. The key idea here is the formula, which is m equals the average of the x-coordinates and the average of the y-coordinates of the 2 endpoints. Specifically, we write it as m equals x1 plus x2 divided by 2, y1 plus y2 divided by 2. This means to find the midpoint, we just need to calculate the average of the x values and the average of the y values separately. Now let's go through an example to make this clearer. Suppose our endpoints are at -1, 4, and 3, -2. To find the x-coordinate of the midpoint, we add the x values, -1 plus 3, which gives us 2. Then we divide that by 2, resulting in 1. For the y-coordinate, we add 4 and -2, which gives us 2, and dividing by 2 again, we get 1. So the midpoint between these 2 points is at 1, 1. This averaging process is important because it guarantees that the midpoint is exactly halfway between the 2 endpoints, meaning it's equidistant from both. To double-check your work, you can calculate the distance from each endpoint to the midpoint. They should be equal, confirming that you've correctly found the midpoint and that it truly balances the segment. This concept ties into the overall theme of understanding geometric relationships and how to work with coordinates effectively. Let's explore the equation of a circle. A circle, simply put, is the set of all points in a plane that are the same distance from a fixed point, which we call the center. This distance is the radius. In coordinate geometry, we can express this relationship with an algebraic equation. The standard form of a circle's equation not only shows us where the center of the circle is, but also tells us the length of its radius. This makes it a very useful tool for graphing and analyzing circles. Understanding these equations is really important because they have practical applications in many fields, like GPS technology, computer graphics, and even physics simulations involving circular motion. As we go through this presentation, keep in mind how these concepts connect to real-world uses and the bigger picture of math in everyday technology. Let's take a closer look at the equation of a circle in its standard form. The general formula is xh2 plus yk2 equals r2. Here, k represents the center of the circle and r is the radius. This form is really useful because it clearly shows the center point and the radius, which are key to understanding the circle's position and size. Now let's consider an example. Suppose our center is at 1 minus 2 and the radius is 3. When we substitute these values into the formula, we get x, 1, 2 plus y, minus 2, 2 equals 32. Simplifying the second term, that becomes x, 1, 2 plus, y plus 2, 2 equals 9. It's important to notice how the signs work in this equation. Since the y-coordinate of the center is negative, we write it as y plus 2 in the equation. This might seem a bit counterintuitive at first, but it follows the rule that if the coordinate is negative, it becomes positive inside the parentheses. And remember, the radius squared is always on the right side of the equation. This equation tells us that any point x, y, that satisfies it is exactly 3 units away from the center point 1, minus 2. So every point on the circle maintains that fixed distance, which is the radius. Understanding this form helps us visualize and work with circles more effectively, especially when graphing or solving problems involving circle geometry. Let's take a closer look at the shift of the absolute value function. As you know, function transformations give us a powerful way to modify a basic parent function, like shifting it left or right, stretching or compressing it, or even reflecting it across an axis. Think of these transformations as a kind of map, helping us understand exactly how changes in the equation influence the graph. The absolute value function is particularly great for this because of its clear V-shape. That makes shifts and other transformations easy to visualize. When we shift the graph, we're essentially moving this V-shape either horizontally or vertically without changing its shape. Understanding these transformations helps us see the bigger picture, how algebraic changes relate to the graph's appearance. It's like learning the language of the graph, so we can predict what happens when we tweak the equation. This foundational idea will carry us through more complex transformations later on, but starting with the absolute value function gives us a clear and intuitive example. Let's take a closer look at the shift of the absolute value function. The parent function y equals x creates a characteristic V-shaped graph with its vertex at the origin, which is the point 0, 0. This is our starting point before we apply any transformations. Now, when we consider the horizontal shift, the expression x minus 3 shifts the graph to the right by 3 units. Remember, if there's a minus inside the absolute value, it means we move the graph to the right, and if there were a plus, it would shift it left. Next, the vertical shift involves adding a plus 2 outside the absolute value. This moves the entire graph up by 2 units. Adding outside shifts the graph upward, while subtracting outside would move it downward. So putting it all together, the final transformed function y equals x minus 3 plus 2 positions the vertex at the point 3, 2. This means the graph has been shifted right by 3 units and up by 2 units from the original vertex at the origin. Understanding these shifts helps us see how modifications inside and outside the absolute value affect the graph's position, which is key in graph transformations overall. Let's talk about odd functions and their unique properties. An odd function has a special kind of symmetry called origin symmetry. This means that if you rotate the graph 180 degrees around the origin, it looks exactly the same as the original graph. This symmetry is quite important because it appears in various fields like mathematics, physics, and engineering. Mathematically, we say a function is odd if it satisfies the condition that f negative equals negative f for every in its domain. In simple terms, if you plug in the negative of any input, you'll get the negative of the output you'd get for the positive input. For example, if f of 2 equals 8, then f of negative 2 must equal negative 8. Some common examples of odd functions include f of x equals x cubed, x to the fifth power, and sine of x. You'll notice that these functions often pass through the origin because at x equals 0, the output is 0, which aligns with the odd function condition. Understanding odd functions helps us see the symmetry and behavior of different mathematical models, making them fundamental in analyzing various phenomena across different disciplines. Let's delve into the concept of odd functions. An odd function has a specific property, f(x) equals negative f(x). In other words, if you replace x with x, the function's value becomes its negative. This property leads to a kind of symmetry called origin symmetry, meaning the graph looks the same when rotated 180 degrees around the origin. Some common examples of odd functions include f(x) equals x cubed, sine of x, and just plain x. Recognizing these helps us understand how they behave across different domains. Now, contrasting that, we have even functions. These satisfy the property that f(x) equals f(x). So, if you plug in x, the output remains the same. This results in symmetry about the y-axis. Think of the graph being mirrored across the y-axis. Examples include squared, cosine of x, and the absolute value of x. It's important to note that many functions aren't strictly even or odd. For example, a function like x squared plus 1 doesn't satisfy either symmetry condition because it doesn't mirror across the axes in that way. Understanding whether a function is even, odd, or neither can be incredibly useful. It helps us interpret the function's behavior more intuitively and can even simplify calculations when analyzing these functions or sketching their graphs. Recognizing these symmetries is a key step in mastering function analysis. Let's talk about the inverse of a linear function. The key idea here is that an inverse function essentially undoes what the original function does. So, if a function takes an input and produces an output, the inverse takes that output and gives us back the original input. Graphically, this relationship is visualized as a reflection across the line y equals x. Imagine folding the graph along that line. Your original function and its inverse would line up as mirror images. Finding inverses is really important because it helps us solve equations more easily and understand how different functions relate to each other. Not every function has an inverse, but linear functions always do, which makes them a perfect starting point for learning about this concept. So, in the context of our overall theme, understanding inverses deepens our grasp of how functions work and interact, especially when it comes to solving real-world problems. Let's start with the original function, which is f of x equals 2x plus 1. To make it easier to work with, I'll replace f of x with y, giving us y equals 2x plus 1. Next, we swap the variables to find the inverse. So, we exchange x and y, resulting in x equals 2y plus 1. This step is crucial because it reflects the inverse relationship we're trying to determine. Now we solve for y. To do that, we isolate y by subtracting 1 from both sides, giving us x minus 1 equals 2y. Then, we divide both sides by 2, which yields y equals x minus 1 over 2. Finally, we write the inverse function. It's f inverse of x equals x minus 1 divided by 2. To verify, we compose the original function with its inverse and check if the result simplifies to x. If it does for all x, then we've successfully found the correct inverse. This process highlights the key idea. Finding the inverse involves swapping variables, solving for the new output, and verifying the result. It's a fundamental skill that helps us understand how functions and their inverses relate to each other within the broader context of functions and transformations. Let's talk about the axis of symmetry for a parabola. Every parabola has a vertical line of symmetry that passes right through its vertex. Think of it as a mirror line that divides the parabola into two mirror image halves. This axis is really important because it helps us understand how the parabola behaves and is key to solving quadratic problems. Imagine folding the graph along this line. You'd see that both sides match up perfectly, which highlights how symmetrical the parabola is. The axis of symmetry isn't just a visual tool, it actually helps us locate the vertex, which is the highest or lowest point of the parabola. It also allows us to find the maximum or minimum values of the quadratic function, and it gives us a clearer picture of the parabola's overall shape and where it sits on the coordinate plane. In essence, understanding this axis of symmetry is fundamental for analyzing and working with parabolas effectively. Let's take a closer look at the axis of symmetry for a parabola, specifically when it's written in vertex form. The equation y equals a times the quantity minus h squared plus k clearly shows us the key features of the parabola. First, notice that the vertex of the parabola is located at the point h, k. This point is really important because it represents the turning point of the parabola, either its highest point if it opens downward, or its lowest point if it opens upward. Next, the axis of symmetry is the line equals h. Think of it as a vertical line that passes right through the vertex. This line effectively divides the parabola into two mirror image halves. For example, if we have y equals 2 times the quantity x minus 3 squared plus 5, then the vertex is at the point 3, 5. The axis of symmetry in this case is the line equals 3. What's really interesting is that every point on the parabola has a corresponding point on the opposite side of this line, at the same distance away. This symmetry is fundamental to understanding how parabolas behave and helps us analyze their properties more easily. So, in essence, the vertex gives us the key coordinate, and the axis of symmetry helps us understand how the parabola is balanced around that point. This concept ties directly into our overall goal of mastering the features of quadratic functions and their graphs. Let's talk about the vertical asymptotes of rational functions. These functions are fractions where both the numerator and the denominator are polynomials. Now, an important thing to remember is that these functions can have what we call vertical asymptotes, which are invisible vertical lines that the graph approaches but never actually touches or crosses. When the graph gets close to these lines, the function's value shoots up toward positive or negative infinity, indicating a kind of boundary or limit. Now, where do these vertical asymptotes come from? They occur specifically at the x values where the denominator equals 0, but the numerator doesn't. In other words, at these points, the function is undefined because dividing by 0 is impossible. Recognizing these points is key to understanding how the graph behaves near these lines. It's also helpful to distinguish between asymptotes and x-intercepts. When the numerator equals 0, but the denominator doesn't, we get x-intercepts, points where the graph crosses the x-axis. So, while zeros of the numerator give us the x-intercepts, zeros of the denominator give us the vertical asymptotes. Understanding where these asymptotes are located is essential for graphing rational functions accurately and predicting their behavior, especially near those critical x values where the function tends toward infinity. This knowledge ties directly into the overall theme of analyzing and sketching rational functions with confidence. Let's take a closer look at the square root function. Essentially, it takes any number and returns a value which, when multiplied by itself, gives back that original number. For example, the square root of 9 is 3 because 3 times 3 equals 9. The basic way to write this function is f(x) equals the square root of x, which we write as square root x. Now, an important point is about the domain, or the set of possible inputs for this function. It includes all numbers that are greater than or equal to 0. Why? Because in the real number system, you can't take the square root of a negative number and get a real result. So, the function only works for values starting from 0 and going up. If you look at the graph, it starts right at the origin, at the point 0, 0, and then curves upward to the right. You'll notice that as x increases, the slope of the graph gets less steep. That means the function grows, but at a decreasing rate. In fact, the square root function grows more slowly than linear functions like y equals x, while y equals x increases by 1 for each step increase in x. The square root function's increase becomes smaller and smaller as x gets larger. This is what gives it that characteristic curved shape, distinguishing it from a straight line. So, understanding this helps us see how the square root function behaves and how it fits into the bigger picture of mathematical functions and their graphs. When working with square root functions, it's important to understand their domain, which is the set of x values that produce real number outputs. To find this domain, we need to identify which x values make the expression inside the square root, known as the radicand, greater than or equal to 0. This is because the square root of a negative number isn't a real number. It's what we call an imaginary number, and that's not part of basic algebra. So the key point here is that the radicand must be non-negative to ensure our function outputs real numbers. This restriction is crucial in understanding the behavior of square root functions and helps us determine their domain accurately. Let's take a closer look at the domain of the square root function, specifically for the function f(x) equals the square root of x minus 4. Our goal here is to find all the x values that make this function valid. To do that, we start by setting up an inequality. X minus 4 should be greater than or equal to 0. This makes sense because the radicand, or the expression inside the square root, must be non-negative for us to get real outputs. When we solve for x, we add 4 to both sides, which gives us is greater than or equal to 4. Now, in terms of notation, we write the domain as 4, infinity. This notation might look a bit technical, but it just means that all real numbers starting from 4 and going up to infinity are included. The square bracket around 4 indicates that 4 itself is part of the domain, meaning can be exactly 4, or any number larger than that, like 5 or 100. The parenthesis next to infinity tells us that infinity is not a specific number we can reach, but rather a concept representing unbounded growth. Understanding this helps us see which x values are valid for this function, and it ties into the overall theme of analyzing the domains of different functions, ensuring we're working within the correct constraints for real-valued outputs. Understanding logarithms is essential because they answer a fundamental question. To what power must the base be raised to get a certain value? Think of it as the inverse of exponentiation. Just like division is the inverse of multiplication, logarithms undo what exponents do. Now, the formal definition is that log a equals c if and only if b raised to the power of c equals a here. B is the base, a is the argument, and c is the result. For example, when we ask log 3, 9, we're asking 3 raised to what power equals 9. Since 3 squared is 9, we know the answer is 2. So log 3, 9 equals 2. Logarithms are incredibly useful across many fields: science, engineering, finance, because they help us deal with exponential growth and decay, measure earthquake magnitudes, calculate compound interest, and even compress large amounts of data. Overall, understanding how logarithms work helps us interpret and solve real-world problems involving exponential relationships, which is a key part of the overall theme of this presentation. Let's look at this example involving exponential equations. So the problem states that x equals 5, and our goal is to solve for x. The tricky part here is that is in the exponent position, which means we need to use a special approach. The key idea is to use the natural logarithm, or ln. Because it's the inverse of the exponential function with base, e, this means that applying ln to both sides will help us isolate x. Step by step, we take ln of both sides. ln of e raised to the x equals ln of 5. Now, since ln and e are inverse functions, ln of ex simplifies directly to x. So now we have x equals ln of 5. To get a numerical value, we can use a calculator, which gives us approximately 1.609. It's important to understand that the natural logarithm, ln, is specifically the logarithm with base e, which is approximately 2.71828. This constant e appears all throughout mathematics, science, and even in nature, making ln one of the most commonly used logarithms in advanced math. So, in summary, whenever you're dealing with exponential equations like this, applying the natural logarithm is a powerful tool to help you solve for the variable in the exponent. Let's walk through solving an exponential equation step by step. Suppose we start with the equation ex equals 5. Our goal is to find the value of x to do this. The first step is to apply the natural logarithm, or ln, to both sides of the equation. So we write ln ex equals ln 5. Now, here's where the key property comes into play. Since ln and e are inverse functions, ln ex simplifies directly to x. This leaves us with equals ln 5. And if we evaluate ln 5, we get approximately 1.609. The important concept here is that the natural logarithm, or ln, is the perfect tool for solving equations where the variable appears as an exponent with base e, because ln and e are inverse functions. They undo each other, allowing us to isolate easily. This technique isn't limited to just this example. It works for any exponential equation with base e. It's a powerful method that helps us solve for the variable in the exponent quickly and effectively. Let's look at solving a simple exponential equation. Our starting point is the equation for x equals 16. Our goal here is to find out what value of x makes this true. The first key point is to recognize a pattern. Notice that 16 can be written as 4 squared, or 4 to the power of 2. When we see that, it gives us a useful clue. Both sides of the equation now have the same base, which is 4. Next, we rewrite the equation as 4 raised to the power of x equals 4 squared. This step is important because now both sides of the equation have the same base, making the comparison much simpler. The next move is to set the exponents equal to each other. Since the bases are the same, the exponents must be the same for the equation to hold true. So, x equals 2. This method works whenever you can express both sides of an exponential equation with the same base. It's often faster and more straightforward than using logarithms. Remember, always check if the numbers are related by powers before jumping into logarithmic methods. This can save you some time and effort. Let's talk about the period of sinusoidal functions, focusing on the general sine function, y equals sine of bx. The key point here is that the coefficient b influences how quickly the function completes one full cycle. Essentially, as b changes, it affects the frequency of the wave. Now, to find the period of this function, we use the formula. Period equals 2 pi divided by the absolute value of b. This tells us the horizontal distance needed for the sine wave to complete one full oscillation before it starts repeating. For example, if we look at y equals sine of 2x, here b is 2. Plugging that into our formula, the period becomes 2 pi divided by 2, which simplifies to pi. That means, instead of the usual 2 pi, this function completes a full wave in just pi units. This concept is important because the period essentially measures how long it takes for the wave to repeat itself. When b is larger, the period gets smaller, so the wave oscillates more frequently. Conversely, with a smaller b, the wave stretches out and completes a cycle over a longer distance. Remember, the standard sine function has a period of 2 pi, which is the distance it takes to complete one full cycle before repeating. So, understanding how the coefficient b impacts the period helps us analyze and predict the behavior of sinusoidal functions more effectively. Let's look at how to convert radians to degrees. The key here is knowing the formula. Degrees equals radians multiplied by the conversion factor, which is 180 degrees divided by pi. This factor bridges the two measurement systems, since we know one full circle is 360 degrees or 2 pi radians. Next, we identify our given angle. In this case, it's 4 pi over 3 radians. We'll multiply this by our conversion factor to get the angle in degrees. Now, when we do the multiplication, it looks like this. 4 pi over 3 times 180 degrees over pi. Notice that the pi cancels out, simplifying the expression to 4 times 180 degrees over 3, which equals 720 degrees over 3. Finally, we perform the division. 720 divided by 3, and that gives us 240 degrees. So, our answer in degrees is 240. Remember, radians and degrees are just two ways of measuring angles. Since we know that 4 pi over 3 radians is more than pi, which is 180 degrees, but less than 2 pi, which is 360 degrees, 240 degrees makes perfect sense within that range. Always double-check that your answer fits the context, and you'll keep your conversions accurate and meaningful. Let's take a moment to talk about verifying our radian conversions. It's always helpful to remember some common radian values and their degree equivalents. For example, pi/4 radians is 45 degrees, pi/2 radians is 90 degrees, and 3 pi/4 radians equals 135 degrees. Similarly, pi radians is 180 degrees, 4 pi/3 is 240 degrees, and 3 pi/2 is 270 degrees. These serve as useful benchmarks when you're converting between radians and degrees. When you're doing a conversion, it's a good habit to double-check your work by comparing your answer to these known values. For instance, if you're converting 3 pi/4 radians, you can do the calculation. 3 pi/4 times 180 degrees over pi, which simplifies to 135 degrees. And that matches our reference value, confirming that your conversion is correct. Another important point is to always read the problem carefully. Slight differences in the fractions, like 4 pi/3 versus 3 pi/4, can lead to very different degree measures. For example, 4 pi/3 radians is 240 degrees, whereas 3 pi/4 radians is only 135 degrees. Paying close attention to the exact fractions ensures you don't make mistakes in your conversions. So, to summarize, always verify your conversions against these benchmarks, and read each problem carefully to catch any small differences that can have a big impact. This careful approach helps ensure accuracy and confidence in your work as you continue with your studies. Let's walk through solving for the angle when the tangent value is given. So, we start with the given information. Tan of theta equals -1, and we know that theta is in the second quadrant. Now, it's important to remember the signs of tangent in different quadrants. Tangent is negative in quadrants II and IV, and positive in quadrants I and III. Since our tangent is negative, our angle must be in either quadrant II or IV. Next, we look at the reference angle. When tan of theta equals 1, that corresponds to an angle of 45 degrees, or pi over 4 radians. This is our key starting point because the tangent of 45 degrees is 1. Now, since we need a tangent of -1, and we're in the second quadrant, we find the angle by subtracting the reference angle from pi. So, pi minus pi over 4 gives us 3 pi over 4, which is 135 degrees. This angle, 3 pi over 4, has a tangent of -1 and is located in the second quadrant. Remember, in the second quadrant, angles range from pi over 2 to pi, or 90 to 180 degrees. By subtracting our reference angle from pi, we find the exact angle in that range that satisfies our tangent condition. So the angle we're looking for is 3 pi over 4, or 135 degrees. Let's take a closer look at the Pythagorean identity, which states that sin squared of x plus cos squared of x equals 1. This is one of the most fundamental relationships in trigonometry, and what's great is that it holds true for all real values of x. That universality makes it incredibly powerful for simplifying expressions and solving equations. Now, where does this identity come from? It actually stems directly from the Pythagorean theorem, but applied to the unit circle. Think about any point on the unit circle at an angle. The coordinates of that point are cos x, sin, and since it's on the circle, the distance from the origin is always 1. Applying the Pythagorean theorem here, we get that the square of the x-coordinate plus the square of the y-coordinate equals 1 squared. That's where the identity comes from. So, how do we use this in practice? When you see a complex trigonometric expression, you can use this identity to simplify it. For example, if you see sin squared in an expression, you can replace it with 1 minus cos squared. Conversely, if you see cos squared x, you can substitute it with 1 minus sin squared. This substitution technique is a crucial tool for solving more complicated trigonometric equations efficiently. Overall, understanding this identity not only helps simplify problems, but also deepens your grasp of the relationships between sine and cosine. It's a cornerstone in the broader theme of simplifying trigonometric expressions, making your problem-solving process much smoother and more intuitive. Now, let's take a closer look at the amplitude of trigonometric functions. In the general form, we have y equals a sine of x or y equals a cosine of x. The key point here is that the coefficient a determines the amplitude of the wave. The amplitude itself is simply the absolute value of a, which we write as amplitude equals a. This value tells us the peak height of the wave from its center line, or midline. In practical terms, the amplitude measures the maximum displacement from equilibrium. For example, if we have y equals 3 cosine of x, the amplitude is the absolute value of 3, which is 3. This means the wave oscillates 3 units above and 3 units below the center line, giving a total vertical span of 6 units. Understanding amplitude is really important across various fields like physics, engineering, and signal processing. Larger amplitudes indicate more intense oscillations. Whether we're talking about sound waves, light waves, or ocean waves, the amplitude helps us grasp the wave's energy and behavior. Let's take a closer look at evaluating the inverse sine function, or arcsin. So what does arcsin x ask? It asks, what angle has a sine of x? For example, if we see arcsin 1, we're trying to find the angle theta where sin theta equals 1. Now recall our basic sine values. Sin of pi over 2, or 90 degrees, is 1. That's a key point to remember. So in this case, arcsin 1 means, what angle theta has sin theta equal to 1? The answer is pi over 2, or 90 degrees. But here's an important concept about the inverse sine function itself. The inverse sine, also called arcsine, is defined with a restricted range, from negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. This restriction is crucial because it ensures that each input corresponds to exactly one output, making the function well-defined. Within this range, pi over 2 is the only angle whose sine equals 1. That's why, when we evaluate arcsin 1, our answer is pi over 2. And remember, even though sine of pi over 2, 5 pi over 2, or 9 pi over 2 all equal 1, the arcsin function only returns the principal value within its defined range. That means it always gives us the unique, most standard answer. So, in summary, the inverse sine function helps us find the specific angle in a restricted range where the sine is a given value. It's a powerful tool, but understanding its range and principal values is key to using it correctly. Let's take a look at the law of cosine's formula. C squared equals a squared plus b squared minus 2 times a times b times cosine of c. This formula is really powerful because it relates the lengths of a triangle's sides to the cosine of one of its angles. And what's great about it is that it works for any triangle, not just right triangles, so it's a more general version of the Pythagorean theorem. Now you would use the law of cosines when you know 3 sides, what we call SSS, or 2 sides and the included angle, which is SAS. This formula helps you find unknown sides or angles, so it's really versatile for solving various triangle problems. And here's a neat special case. When angle C is 90 degrees, cosine of C is 0, so the formula simplifies down to the Pythagorean theorem. That shows how the law of cosines extends the Pythagorean theorem to non-right triangles, making it an essential tool in our toolkit. Let's take a closer look at this conic section. The given equation is 4x2 plus 9y2 equals 36. This represents a general form of a conic, which means it can describe different shapes depending on how we manipulate it. To identify the specific conic, we first convert it to its standard form by dividing everything by 36. When we do that, we get x2 divided by 9 plus y2 divided by 4 equals 1. This step is crucial because standard forms make it easier to recognize the shape. Now, looking at this form, we see it matches the pattern for an ellipse. x2 over a squared term plus y2 over another squared term equals 1. And importantly, both coefficients are positive, but they are different, which tells us something about the shape. So what does this mean for the graph? It indicates that the shape is an ellipse centered at the origin. The horizontal radius, or the semi-major axis, is 3, since the square root of 9 is 3. The vertical radius, or semi-minor axis, is 2, because the square root of 4 is 2. To wrap up, remember that an ellipse can be thought of as a stretched circle. When the coefficients of x2 and y2 are both positive but not equal, the result is an ellipse. And if those coefficients were equal, we'd be dealing with a perfect circle. This understanding helps us quickly categorize and sketch conic sections based on their equations. Let's talk about finding the vertex of a parabola using the vertex form. The general form looks like this: y equals x minus h squared plus k. This form is really handy because it immediately shows us the vertex's location at the point hk. For example, if we have the equation y equals x minus 2 squared plus 3, we can directly compare it to the vertex form. From this, we see that h equals 2 and k equals 3. So the vertex is at the point 2, 3. One important thing to remember is that the sign in front of the h inside the parentheses flips when identifying the vertex. If the equation shows x minus 2, then the x-coordinate of the vertex is positive 2, not negative 2. The vertex is a crucial point because it represents either the minimum or maximum of the parabola. Since in our example the coefficient of x minus 2 squared is positive, the parabola opens upward, making this point a minimum. This form really simplifies graphing because you can easily identify the vertex and understand the parabola's overall shape just by looking at the equation. Let's take a closer look at the dot product of vectors, starting with the notation. When we write u equals u1, u and v equals v1, v, we're simply representing two vectors in a two-dimensional space with their components. The key formula for the dot product is uv equals u1 v1 u2 v2. This means we multiply the corresponding components of the vectors and then add those products together. Now, it's important to remember that the result of a dot product is a scalar, not a vector. It's just a single number. For example, if u equals 3, 4, and v equals 2, 1, then the dot product is 3, 2 plus 4, 1, which equals 6 plus 4, giving us 10. The dot product is a very useful tool because it helps us find angles between vectors, using the formula uv equals uv cos theta, where theta is the angle between the vectors. It also allows us to check if two vectors are perpendicular. If their dot product is 0, then they are orthogonal. Additionally, it helps us find the projection of one vector along another, which is useful in many applications. So, understanding the dot product gives us a powerful way to analyze the relationships between vectors, whether we're measuring angles, checking perpendicularity, or projecting vectors onto each other. Let's walk through converting polar coordinates to rectangular coordinates with this example. We start with the given polar coordinates, which are r equals 4 and theta equals 6 pi. Remember, r represents the distance from the origin, and theta is the angle measured from the positive x-axis. To convert, we use the formulas equals r times cosine of theta and y equals r times sine of theta. Now, since our angle is 6 pi, we need to simplify it because trigonometric functions repeat every 2 pi radians. Notice that 6 pi is 3 full rotations of 2 pi each, which brings us back to an angle of 0. So, cosine of 6 pi is the same as cosine of 0, which is 1, and sine of 6 pi is the same as sine of 0, which is 0. Plugging these into our formulas, x equals 4 times 1, which equals 4, and y equals 4 times 0, which equals 0. Therefore, the rectangular coordinates are 4, 0. This example highlights an important concept. Because trigonometric functions are periodic, angles differing by multiples of 2 pi represent the same point. So, even though the angle was 6 pi, the point is located 4 units along the positive x-axis, just like at 0 radians. This illustrates how understanding the periodic nature of these functions helps us convert and interpret polar coordinates effectively. Let's talk about the determinant of a 2 times 2 matrix. When we have a matrix in this form, with elements A, C, B, and D arranged like this, A, C, B, D, the determinant is calculated as add minus BC. This simple formula actually holds a lot of significance. The determinant is a scalar value, which means it's just a number, but that number tells us important things about the matrix. For example, if the determinant is not 0, meaning det not equal to 0, then the matrix is invertible. That means you can find its inverse, and it has certain properties that are useful in solving equations and understanding transformations. On the other hand, if the determinant equals 0, det equals 0, the matrix is not invertible. It essentially means the transformation it represents collapses space in some way, losing information. Another key point is that the absolute value of the determinant, det, represents how the transformation scales area. So if the determinant is 2, it indicates that areas are doubled after the transformation. Conversely, a determinant of 0.5 means areas are halved. This idea of area scaling is crucial because it helps us visualize how the matrix affects space, whether it stretches, shrinks, or flips it. Understanding this concept is fundamental in solving systems of equations and analyzing linear transformations, as it gives us insight into how the matrix manipulates geometric space. Let's take a look at the partial fraction decomposition form. We start with our original expression, which is a rational function with a denominator of x times x minus 1. The goal here is to break this complex fraction into simpler, more manageable parts. So, we rewrite it in a form where each factor in the denominator gets its own fraction. In this case, it becomes a over x plus b over x minus 1. This process is called partial fraction decomposition, and it's really useful because it simplifies many problems, especially when we're integrating functions in calculus or solving certain equations. The key idea is that each linear factor in the denominator contributes one term to the decomposition. So, for each factor, we assign a constant numerator, like a or b, and then find those constants. To find a and b, we multiply both sides of the equation by the common denominator, which is x times x minus 1, and then solve for these constants. For example, if we have 5 over x times x minus 1, we set it equal to a over x plus b over x minus 1, and then clear the denominators by multiplying through. This allows us to compare coefficients or plug in convenient values of x to find the constants. Overall, partial fraction decomposition breaks down complex fractions into simpler pieces, making them much easier to work with, especially in calculus and algebra. Now, let's talk about inconsistent systems of linear equations. A system is considered inconsistent when it has no solutions at all. This usually happens when the equations represent lines that are parallel but never intersect. In other words, there's no single point that satisfies all the equations simultaneously. If we look at it graphically, these lines are distinct and parallel. They have the same slope but different y-intercepts. So, they run alongside each other without crossing. Algebraically, this inconsistency shows up when the equations contradict each other. For example, consider the equations x plus y equals 5 and x plus y equals 3. Since both can't be true at the same time, the system has no solution. Why does this matter? Well, recognizing when a system is inconsistent saves us a lot of time and effort. If we know there's no solution, we don't waste resources trying to find one. In contrast, a consistent system has at least one solution. It might have exactly one, like intersecting lines, or infinitely many, like coincident lines. Spotting inconsistency early is key to avoiding futile attempts to solve the system. Let's take a closer look at the binomial theorem coefficient formula. The formula is nck equals n factorial divided by k factorial times n minus k factorial. This formula helps us find the coefficients when we expand expressions like x plus y raised to the nth power. Each term in that expansion has a coefficient determined by this binomial coefficient, sometimes called n choose k. Now, understanding factorials is key here. Recall that n factorial, written as n, is the product of all positive integers from n down to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which equals 120. And 3 factorial is 3 times 2 times 1, giving us 6. Interestingly, by definition, 0 factorial is 1. Let's apply this to an example. Suppose we want to find the coefficient of the term x squared y cubed in the expansion of x plus y to the 5th power. We use the formula 5c3, which is 5 factorial divided by 3 factorial times 2 factorial, since 5 minus 3 is 2. Calculating that, we get 120 divided by 6 times 2, which simplifies to 10. Finally, it's worth noting that binomial coefficients are visually represented in Pascal's triangle. They also appear frequently in combinatorics, probability, and algebra. An interesting property is their symmetry. NCK equals NC, n minus k. This symmetry creates the mirror image pattern we see in Pascal's triangle, connecting all these concepts together in a really elegant way. Let's break down the sum of a finite arithmetic sequence using this handy formula. Sn equals n divided by 2, multiplied by the sum of the first term, a 1, and the last term, n. First, a 1 represents the very first term of our sequence. It's where everything begins, so understanding a 1 helps us set the starting point for our calculations. Next, we have n, which is simply the number of terms we're adding up. For example, if we're summing the first 10 terms, then n equals 10. This tells us how far into the sequence we're going. Then there's n, the last term we're including in our sum. In an arithmetic sequence, we can find this using the formula n equals a 1 plus n minus 1 times the common difference d. Now, the beauty of this formula is that it calculates the sum quickly by taking the average of the first and last terms, which is a 1 plus n divided by 2, and then multiplying that average by the total number of terms, n. This approach is much faster than adding each term individually, especially when dealing with long sequences. It connects the idea of averaging the endpoints to find the total sum efficiently, an essential concept when working with arithmetic sequences in broader mathematical contexts. Let's look at the magnitude of a vector. Suppose we have this vector v, which is 3 minus 4. The magnitude or length of this vector tells us how long it is from the origin to the point 3 minus 4. The formula for the magnitude is v equals the square root of the sum of the squares of its components. In symbols, that's square root, v2 plus v22. This comes directly from the Pythagorean theorem, which is a fundamental relation in geometry that relates the lengths of the sides of a right triangle. Now let's do a step-by-step calculation. First, we square each component. 3 squared is 9, and negative 4 squared is 16. Then we add those together, giving us 25. Taking the square root of 25 gives us 5. So the magnitude of this vector is 5. It's important to remember that the magnitude, sometimes called the length or the norm, of a vector represents its size or how far it is from the origin. You can think of it as the length of the arrow when you draw it from 0, 0 to 3, minus 4. And importantly, the magnitude is always non-negative. It can't be negative because it's a measure of distance. Understanding the magnitude is crucial, especially in physics, where it helps us calculate speeds, forces, and distances. In geometry, it helps us find unit vectors, which are vectors with a length of 1, and to normalize other vectors to have a length of 1 for various applications. Understanding limits of functions is really fundamental to calculus. The idea of a limit helps us understand how a function behaves as the input gets close to a specific value. It's important to note that this behavior might be different from the actual value of the function at that point, or even the function might not be defined there at all. When we write lim x approaching c of f of x equals L, we're saying that as x gets closer and closer to c, the values of f of get closer and closer to L, but for this limit to exist, the key is that the approach from the left and from the right should lead to the same value, L. An important point to remember is that the function doesn't have to be defined exactly at equals c for the limit to exist. What matters is how the function behaves nearby, around that point. This concept is really crucial when we're talking about continuity and when we start calculating derivatives. Limits also give us a rigorous way to define instantaneous rates of change, like slopes of tangent lines and areas under curves, especially when the functions have discontinuities or asymptotes. So understanding limits really opens the door to many key ideas in calculus. Let's talk about what it means for a function to be continuous at a point. First, the function must be defined at that point. That means f, c, has to actually exist, so there's no whole or undefined spot at equals c next. The limit of the function as x approaches c must exist. In other words, as we get closer from both sides, the values of f, x, should approach the same finite number. And third, the limit as x approaches c has to be equal to the actual function value at c, so limx right arrow cf, x, must equal fc. Think of continuity like drawing the graph without lifting your pencil. If all three conditions are met, you can do that smoothly through that point. If any of these conditions fail, then we say the function has a discontinuity there, which could look like a break, a hole, or a jump. So, ensuring all three are satisfied is key to understanding where a function is continuous. Let's talk about derivatives and what they actually mean. The derivative of a function at a specific point is essentially the slope of the tangent line to the graph at that point. It tells us how the function is changing right at that moment, giving us the instantaneous rate of change. Geometrically, this means the derivative shows us how steep the graph is at any given point, and whether it's moving upwards or downwards, or to the left or right. It's like understanding the direction and speed of the graph's slope at that exact spot. From a physical perspective, if we think of a function like position over time, then its derivative, often called velocity, indicates how fast the position is changing at any moment. So, the derivative bridges the gap between the shape of the graph and real-world motion. When we write derivatives, you'll see notations like f prime, di/dx, or df/dx. All of these represent the same core idea, the derivative of a function with respect to x. Derivatives are the building blocks of differential calculus. They help us find maximum and minimum points, analyze motion, optimize solutions, and model how things change across various fields like science, economics, and engineering. So, understanding derivatives is crucial because they give us powerful tools to analyze and interpret change in many different contexts. Let's explore the integral, which is the fundamental tool for finding the area under a curve over a specific interval. Think of it as a way to sum up infinitely many tiny slices to get the total area. Imagine dividing the space underneath a curve into many thin vertical rectangles. As these rectangles become thinner and we add more of them, the sum of their areas gets closer and closer to the true area under the curve. The notation for an integral looks like this: integral f, x dx. The elongated s, called the integral symbol, stands for sum. The function fx represents the height of the curve at each point, and dx indicates an extremely small width of each rectangle. Integration is essentially the inverse of differentiation. If you have a function f(x) whose derivative is f(x), then integrating f(x) gives you back f(x). Plus a constant c, this relationship is known as the fundamental theorem of calculus, and it beautifully links the ideas of area and change rate. Understanding integrals is crucial because they help us solve problems involving accumulation, like total distance traveled, work done by forces, or the volume of irregular shapes. So, mastering this concept opens up many possibilities in analyzing real-world situations. Let's talk about finding the limits of fractions by substitution. First, when does substitution actually work? Well, if you're looking at the limit as x approaches c for g of x over f of x, it works smoothly if f of c is not 0. In that case, you can just plug in c for x and evaluate directly. It's the simplest method and often the first step. Now, what if substitution doesn't work? That happens when f of c equals 0, meaning the denominator becomes 0. This leads to undefined expressions like 5 over 0 or 0 over 0, which are not valid. When that occurs, we need to use other techniques, such as factoring, rationalizing, or even applying L'Hopital's rule. There's also a special case to keep in mind. If the numerator, g of c, is 0 while the denominator, f of c, is not 0, then the limit is simply 0. We get that by direct substitution. 0 divided by a non-zero number is 0. Remember, direct substitution is often the easiest way to evaluate a limit. Always try it first. If it gives you an indeterminate form like 0 over 0, or infinity over infinity, or results in an undefined expression, then it's time to explore those other methods I mentioned. Now let's talk about one-sided and two-sided limits. First, the left-hand limit, written as limx right arrow c dash f, x, describes how the function behaves as x approaches c from values less than c, or from the left side. The minus superscript simply indicates approaching from below. Similarly, the right-hand limit, written as limx right arrow c plus f, x, looks at the behavior as x approaches c from values greater than c, or from the right side. The plus superscript shows we're approaching from above. The two-sided limit, written as limx right arrow cf, x, exists only when both the left-hand and right-hand limits exist, and importantly, are equal. If these two limits are different, then the two-sided limit simply doesn't exist. One-sided limits are especially important when analyzing discontinuities, like jump discontinuities. In such cases, the function jumps from one value to another, meaning the one-sided limits at that point exist but aren't equal. Because of that, the overall two-sided limit doesn't exist. So, understanding these limits helps us grasp the overall behavior of functions at specific points, especially when functions are not continuous. This insight is crucial for the broader theme of analyzing how functions behave near points of interest. Understanding exponential decay is crucial because it describes many real-world processes where a quantity decreases by a consistent percentage over equal time intervals. The general form of this model is y equals a times b raised to the t, or y equals a, b, t, where the key is that b is between 0 and 1. When b is less than 1, we see decay, meaning the amount gets smaller over time. Let's break down the components. The represents the initial amount, the starting point at time 0, before any decay has taken place. It's the baseline or the original quantity we're observing. The b is called the decay factor, and it tells us what proportion of the quantity remains after each time period. For example, if b equals 0.95, that means 95% of the original remains after each interval, so 5% is lost each time. Then we have t, which stands for time, how many time periods have passed. As t increases, because b is less than 1, the overall y decreases exponentially. This means the quantity shrinks faster at the start and then levels off as it approaches 0, but never quite reaching it. To illustrate, consider the example y equals 500 times 0.95 to the t power. Since 0.95 is less than 1, this clearly shows decay. Each period, 95% of the previous amount remains, and 5% is lost. This is different from exponential growth, where b would be greater than 1, causing the quantity to increase over time instead. Understanding this model helps us analyze many phenomena, from radioactive decay to population decline, where the key idea is a consistent percentage change over equal time intervals. Let's talk about the law of sines applications in triangles. The key formula here is sin. A over A equals sin B over B, which equals sin C over C. What this tells us is that the ratio of a side length to the sine of its opposite angle is constant across the triangle. This is really useful because it allows us to relate sides and angles even when we don't have all the information. Specifically, it's most helpful in cases where we know two angles and one side, what we call ASA, or two angles and the side between them, known as AAS. Now, it's important to remember that the law of sines isn't a catch-all for every triangle situation. For example, if you only know all three sides, what we call SSS, or two sides and the included angle, SAS, you'll want to use the law of cosines instead. Also, there's a tricky case with SSA, where knowing two sides and a non-included angle, because it can sometimes lead to ambiguous solutions. So, understanding when and how to apply the law of sines helps us solve triangles efficiently, but always be aware of its limitations and know when to switch to other methods. Let's talk about symmetry and even functions. A function f(x) is called even if its graph is symmetric with respect to the y-axis. That means if you imagine folding the graph along the y-axis, both halves would match perfectly. It's like the two sides are mirror images of each other. Mathematically, this symmetry is expressed as f(x) equals fx for all in the domain. In other words, plugging in the negative of any input gives you the same output as the original input. Now, to see this in action, consider some examples of even functions. For example, fx equals x squared. If you take x as then minus 3 squared is 9, just like 3 squared. Similarly, for fx equals x to the fourth power, plugging in minus 2 yields 16, the same as plugging in 2. Cosine function is another classic example. Cos of negative x equals cos of x, and the absolute value function, x, is even because 5 equals 5, just like 5. Why does this matter? Well, even functions show mirrored behavior on either side of the y-axis, which is really helpful when analyzing or calculating these functions. Recognizing this symmetry can make our work much easier, reducing the amount of calculation needed and helping us predict how the function behaves without graphing every point. So, understanding even functions is a valuable tool in our mathematical toolkit. Let's take a closer look at the number of permutations formula. It's written as p n k equals n factorial divided by the quantity of n minus k factorial. This formula helps us find the number of ways to arrange k objects chosen from a total of n objects, where order is important. Remember, in permutations, changing the order creates a new arrangement, so ABC is different from BAC. Now let's understand the formula itself. P n k equals n factorial over n minus k factorial. The symbol stands for factorial, which means multiplying all positive integers up to that number. For example, 5 factorial is 5 times 4 times 3 times 2 times 1. Here's a practical example. Suppose you want to find out how many ways you can arrange 3 books on a shelf, chosen from 5 books. So n equals 5 and k equals 3. To solve this, we plug into our formula. P, 5, 3, equals 5 factorial divided by 5 minus 3 factorial. That's 5 factorial over 2 factorial. Calculating further, 5 factorial is 120, and 2 factorial is 2. Dividing 120 by 2 gives us 60. This means there are 60 different ways to arrange 3 books out of 5 on a shelf, considering that the order matters. Permutations are useful in many real-world scenarios, like figuring out race finishing orders, password arrangements, or seating charts. Just keep in mind, when order doesn't matter, we switch to using combinations instead. Understanding geometric sequences is crucial because they help us describe many real-world phenomena. Essentially, a geometric sequence is a list of numbers where each term is found by multiplying the previous one by a fixed number, which we call the common ratio. Or this pattern of multiplying creates exponential growth or decay, depending on the value of r. Now let's talk about the key parameters. The first term, a 1, is simply where the sequence starts. It's our initial value. The common ratio, r, is the constant multiplier between each pair of consecutive terms. To find any term in the sequence without calculating all the previous ones, we use the formula. N equals a 1 times r raised to the power of n minus 1. This makes it much easier to jump directly to any point in the sequence. For example, if we set a 1 to 2 and r to 3, our sequence would look like 2, 6, 18, 54, 162, and so on. Each term is 3 times the previous one, illustrating how the pattern continues. These sequences are powerful because they model many exponential phenomena we encounter daily, like population growth, compound interest in finance, radioactive decay, or even how viral spread occurs. The value of r is key. If r is greater than 1, it indicates growth, meaning the sequence increases rapidly. If r is between 0 and 1, it signifies decay, where the sequence decreases over time. Understanding these concepts helps us analyze and predict behaviors in various fields, making geometric sequences a fundamental tool in mathematics and beyond. Let's walk through how to find the fifth term in this geometric sequence. First, we identify the given information. The first term, a 1, is 2, and the common ratio, r, is 3. Our goal is to find a 5, the fifth term. Next, we apply the general formula for the nth term of a geometric sequence, which is an equals a 1 times r raised to the power of n minus 1. So, in this case, a 5 equals 2 times 3 to the power of 4 because 5 minus 1 is 4. Now we calculate 3 to the power of 4. That's 3 multiplied by itself 4 times. 3 times 3 times 3 times 3, which equals 81. Finally, we multiply 2 by 81, giving us 162. So, the fifth term in this sequence is 162. Using this formula is much more efficient than calculating each term step by step, especially when dealing with larger terms like the 100th. You definitely wouldn't want to multiply 99 times. This approach saves time and reduces the chance of errors, making it essential for working with larger positions in the sequence. Let's take a closer look at the reflection concepts involving logarithmic functions. On this slide, we start with the original function y equals log of x. This is the basic logarithm graph, which increases slowly as x gets larger. You'll notice it has a vertical asymptote at equals 0, meaning the graph approaches the y-axis but never touches it. Now, when we look at the reflected function y equals negative log of x, the negative sign in front creates a reflection across the x-axis. Think of it as flipping the graph upside down. This reflection essentially takes all the y values and makes them their opposites. So, any point above the x-axis, say y equals 2 at a certain x value, now moves below the x-axis to y equals negative 2, and vice versa. This kind of transformation is very useful in modeling situations where behavior is inverted. For example, instead of growth or appreciation, it could represent depreciation or loss. Understanding how reflections work helps us visualize these negative transformations clearly on the graph and see how they relate to the original function. When we're solving systems of inequalities, we're looking for solutions that satisfy all of the inequalities at the same time. Unlike solving a single equation, where the solution is just a point or a line, here the solution is typically a region on the graph. This region represents all the points that meet every inequality's condition simultaneously. This brings us to the idea of the solution set. The solution set is that overlapping area where all the individual inequality regions intersect. Only the points within this shared region satisfy every inequality in the system, making it the true solution space. Now let's talk about the boundaries. Each inequality has a boundary line or curve that defines the edge of its respective region. When we graph these, solid lines indicate that the boundary is included, meaning the inequality uses less or equal to or greater or equal to. Dashed lines, on the other hand, mean the boundary is excluded, corresponding to or. As for the methods to solve these systems, graphical methods involve graphing each inequality and visually identifying the overlapping shaded area. This is often the most intuitive approach. Algebraically, we can also test specific points within the regions to verify whether they satisfy all the inequalities, which helps confirm the solution set. Finally, understanding systems of inequalities is really important in real-world applications like optimization and feasibility analysis. Whether in business, engineering, or economics, they help us define constraints in linear programming problems, guiding us toward the best possible solutions within given limitations. Let's take a closer look at modeling with sinusoidal functions. Sinusoidal functions, which include sine and cosine, are ideal for representing periodic phenomena, things that repeat in regular cycles. Their smooth, wave-like patterns are something we see all around us in nature and technology. For example, consider sound waves. Sound travels through the air as pressure waves that compress and expand the air molecules. These oscillations follow sinusoidal patterns, and here, the frequency of the wave determines the pitch we hear, while the amplitude affects the volume. Another great example is ocean tides. Tides rise and fall in predictable cycles caused by gravitational forces from the moon and sun. When we plot tide heights over time, they form sinusoidal curves, which helps us accurately predict high and low tides. We also see sinusoidal patterns in seasonal cycles. Temperature changes, daylight hours, and plant growth all follow annual patterns. By modeling these with sinusoidal functions, we can better predict seasonal changes and plan accordingly. Now, let's remember that sinusoidal functions are characterized by 4 key parameters: amplitude, which is the height of the peaks; the period, or the length of one complete cycle; the phase shift, which shifts the graph horizontally; and the vertical shift, which moves the midline up or down. These parameters allow us to adapt the basic sine or cosine shape to fit real-world data, making sinusoidal functions invaluable across fields like physics, biology, engineering, and signal processing. So, in essence, understanding these functions gives us a powerful tool to model and analyze many natural and technological phenomena that follow these repeating patterns. Let's explore how we can use the Pythagorean theorem to find the distance between 2 points on a coordinate plane. The key idea here is that the distance formula is actually derived directly from the Pythagorean theorem, showing a beautiful connection between algebra and geometry. Imagine you have 2 points with coordinates x1, y1, and x2, y2. To understand the distance between them, picture forming a right triangle. The horizontal leg of this triangle has a length of the absolute difference in the x-coordinates, which is x2x. Similarly, the vertical leg measures the absolute difference in the y-coordinates, y2y. The hypotenuse, then, is the straight line distance d that we're trying to find. Now, applying the Pythagorean theorem, which states that the sum of the squares of the legs equals the square of the hypotenuse, we get x2, x1, 2 plus y2, y1, 2 equals d2. To solve for d, we simply take the square root of that sum, resulting in the distance formula. D equals the square root of x2, x1, 2 plus y2, y1, 2. This formula is fundamental in coordinate geometry, and you'll see it pop up in many fields, like physics, computer graphics, navigation, and countless other applications. The core idea is that the difference in x-coordinates forms one leg, the difference in y-coordinates forms the other, and the distance between the points is the hypotenuse of that right triangle. Let's look at how to find the x-intercept of a line, starting with our given equation y equals 2x minus 4. This is a linear equation in slope-intercept form, which makes it easier to work with. Now, the x-intercept is the point where our line crosses the x-axis. At this point, the y value is always 0. So to find the x-intercept, we set y equal to 0 in our equation. That gives us 0 equals 2x minus 4. Next, we solve for by adding 4 to both sides, resulting in 2x equals 4. Then, dividing both sides by 2, we find equals 2. So the x-intercept is at the point 2, 0. Remember, when we write the intercepts, we always include the y-coordinate of 0 for the x-intercept. Similarly, the y-intercept is where the line crosses the y-axis, which happens when equals 0. For this equation, plugging in 0 gives y equals minus 4, so the y-intercept is at 0, minus 4. These intercepts are very useful because they help us quickly sketch the graph of the line by marking key points on the coordinate plane. Understanding piecewise defined functions is all about recognizing that a function can have different rules depending on the part of the domain we're looking at. Instead of one single formula applying everywhere, the function's definition changes based on input values. Now, each of these rules or formulas applies to specific intervals within the domain. For example, you might see something like f of x equals x squared when is less than 0, but then f of x equals 2 times when is greater than or equal to 0. This setup allows us to model situations where behavior shifts at certain points. Think about tax brackets, shipping costs, or different rates. These are perfect examples of where piecewise functions shine. When you're evaluating such a function, it's crucial to first figure out which piece applies to your specific input value. That means carefully checking the domain restrictions for each part before doing any calculations. And when we graph these functions, we often notice breaks or jumps at the boundaries where the pieces meet. These discontinuities are a natural part of piecewise functions, highlighting how the behavior changes across different intervals. By understanding these key points, we can better interpret and work with piecewise defined functions in various real-world contexts. Let's look at how to determine the range of a function, using the example of the square root function. F of x equals the square root of x. The range represents all the possible output values the function can produce. For the square root function, since we're taking the square root of x, the outputs are always non-negative. That means you can never get a negative number from square root x when is greater than or equal to 0. So the range includes all real numbers y such that y is greater than or equal to 0. In interval notation, we write this as 0, infinity. The range starts at 0, which happens when equals 0, and then it increases without bound as x increases. The brackets around 0 indicate that 0 is included, while the parenthesis at infinity shows that infinity is not a specific value we can reach. Understanding the range is important because it tells us what outputs to expect from the function. It's especially useful when working with composition of functions, where the output of one function has to fit within the domain of another. Let's talk about how to identify odd functions. The key property of an odd function is that f(x) equals f(x) for every in the domain. What this means in practice is that if you plug in the negative of a number, the output is just the negative of the original output. Visually, this gives the graph a particular kind of symmetry. It's symmetric about the origin. If you rotate the graph 180 degrees around the origin, it looks exactly the same. For example, consider the function f(x) equals x cubed. Let's test the oddness property. f(x) equals x cubed, which simplifies to x cubed. On the other hand, f(x) is negative of x cubed, which is also x cubed. Since these are equal, f(x) equals x cubed is an odd function. Recognizing odd functions is helpful because it helps us understand how the function behaves and can simplify calculations. Some common odd functions include f(x) equals x, x cubed, sine of x, and tangent of x. Now it's useful to contrast this with even functions. Even functions satisfy the property that f(x) equals f(x), which means their graphs are symmetric about the y-axis. For example, f(x) equals x squared or cosine of are even functions. It's also important to note that many functions are neither even nor odd. They don't exhibit any particular symmetry. Recognizing whether a function is odd, even, or neither can really give us insights into its behavior and make working with it much easier.